Hi, everyone. Welcome and thank you for joining us for AstroTours. My name is Simran Nerval, and I'm a PhD student at the University of Toronto, and I will be your host for tonight. I would like to begin tonight's event with a land acknowledgement. So I am tuning in from Kingston, which is situated on the traditional Anishinaabe and Haudenosaunee territory. Our speaker and most of our volunteers are tuning in from Toronto, which is situated on the traditional land of the Huron-Wendat, the Seneca, and most recently, the Mississaugas of Credit River. The territory was subject of the Dish with One Spoon, One Plum Belt Covenant, an agreement between the Iroquois Confederacy and the Confederacy of the Ojibwe and Allied Nations to peacefully share and care for the resources around the Great Lakes. Today, this meeting place is still home to many Indigenous people from across Turtle Island, and I'm grateful to have the opportunity to work on this land. Acknowledging the traditional territory on which we live and work is a small but important step that reminds us to learn more about the Indigenous peoples in this region, to consider the history and ongoing colonialism on this land, and to reflect on how each of us can contribute to reconciliation. We're lucky enough today to have people tuning in from across the country. You can visit native-land and whos.land to learn more about the land that you're on and who it belongs to. So, if this is your first time attending AstroTours, we run our tours generally on the first Thursday of most months. And for today, we'll have our talk by Ajay Gill. After the lecture, we'll be heading over to a Zoom room for a variety of activities and demonstrations, ranging from virtual telescope tours of JWST to showing you how you can use Zooniverse to participate in real science. AstroTours is organized and run by graduate students in the Department of Astronomy and Astrophysics at the University of Toronto, and supported by volunteers who are undergraduate and graduate students in astronomy and physics. We run AstroTours to share our passion, so we really value feedback from our attendees. So after the event, please go to bit.ly/astrotours to give us your feedback. And throughout tonight's talk, please put your questions for Ajay in the YouTube chat. So before we get into tonight's event, I'm just going to go over some upcoming events. So next month, we'll have our February AstroTour. It'll be a lecture by Taylor Kutra about everything from energy production in stars to how to measure distances in the universe and the women who figured it out, inspired by International Day of Women and Girls in Science, which is February 11th, 2022. But this event will be taking place on February 4th at 8 p.m. EST, and it will be online. So events happening from some different organizations would be, there will be an Astro Trivia Night on February 8th at 7 p.m. EST. Visit the Dunlap Institute Facebook page for more information. And there will be a variety of events being held by the Royal Astronomical Society of Canada. Visit their website for more information on that. So now on to tonight's event. Great change. Okay, so tonight's speaker is Ajay Gill. He is a fourth-year PhD student at the David A. Dunlap Department of Astronomy and Astrophysics at the University of Toronto. His research focuses on studying the property of galaxy clusters and their environments. He also works on developing instrumentation for astronomical observations. Outside of work, he likes to play soccer, hiking, history, and travel. I'll now pass it off to Ajay to talk about cosmology with galaxy clusters.
Okay. Sorry, just trying to unmute myself. So thank you, Simran. I'm going to be talking about the research that I work on, cosmology with galaxy clusters. Like Simran said, I'm a fourth-year PhD candidate at the Department of Astronomy and Astrophysics, working with Dr. Barth Netterfield and Dr. Adam Hinks. And before we get started, we can ask the question, what is cosmology? One definition that I like is from a textbook, actually, called Principles of Physical Cosmology by Jim Peebles. And it's the first sentence, actually, of the textbook, and it states, physical cosmology is the attempt to make sense of the large-scale nature of the material around us by the methods of the natural sciences. So before we try to understand, some of the large-scale nature of the universe, of the material world around us, let's try to get a picture of scales in the universe. So currently I'm presenting this from my apartment in Toronto, downtown. And if we zoom out a little bit more from Toronto downtown to the picture by astronaut Chris Hadfield of downtown Toronto, taken from the International Space Station. And we zoom out a little bit further, you can see that now this is the east coast of Toronto, another picture from the International Space Station by astronaut David St-Jacques. And on the east coast, you can see that there's these clusters of light, and they're from our big cities on the east coast. So Toronto, Ottawa, Montreal, and Quebec. And these cities are connected. You can kind of see these highways that are connecting these cities. And these are these sort of like mega cities, and this concept we'll come back to later in the talk. So let's zoom out a bit further. We have this beautiful picture of the planet Earth taken from Apollo 17 in 1972. And now we zoom out a little bit further to an image taken by the Cassini spacecraft, taken from close to the planet Saturn. And you can see that the Earth is right there. This is kind of like, I like to think of it like an updated version of the pale blue dot image. And it's taken at a distance of roughly 1 billion kilometers away from the Earth. So we just went from the orbit of Earth to 1 billion kilometers away, and Earth now appears like a star in this image. Zooming out a bit further, our planet is part of the solar system, and the solar system is part of other solar systems that are part of this galaxy, the spiral galaxy called the Milky Way galaxy. And this picture of the Milky Way galaxy is, of course, an artist's impression of the Milky Way galaxy. And you can see this beautiful spiral structure. And in that image, you can also see our solar system. So we're roughly around there, close to the edge of one of the spiral arms. And now we're talking about even larger distances. So the distance from one side to the other side, or you can think of it as the diameter of the Milky Way galaxy, is 100,000 light years. So now we're not even using kilometers anymore because the zeros get too large. So we're using a unit of distance called light year, and this is how far light will travel in 1 year. And this allows us to, represent large distances in astronomy and cosmology. So we're part of the Milky Way galaxy. The Milky Way itself, we're zooming out a bit further now, is part of the local group. And the local group has two galaxies that are like the primary, more massive galaxies. So we have the Milky Way galaxy where we are, and there's the Andromeda galaxy, or M32. The distance here now, the local group, is 10 million light years. Going back to this picture again, we had 100 light years. Now we have 10 million light years, so it's really, really large distances. The neat thing about the Andromeda galaxy is that even on planet Earth, if you go to a dark enough site, you can actually see the Andromeda galaxy with the naked eye, or even with simple binoculars. It's quite easily visible. You see this fuzzy spot on the night sky, and it's amazing to think that that fuzzy spot has 100 billion stars. So 100 billion solar systems, like the Milky Way galaxy. You're just looking at it in your small field of view in your binoculars. It's really, really fascinating to look at. So we have our local group. We can also see that there's many smaller galaxies around the Milky Way and as well as Andromeda, and these are what we call satellite galaxies. And these are smaller galaxies that are gravitationally bound to the Milky Way or the Andromeda galaxy, including the large Magellanic Cloud or the small Magellanic Cloud that some of you might have heard of. So what if we venture out a little bit further? We know that there are other distant galaxies out there in the universe. So one of the things we can try to do is let's measure the speed and the distance of these distant galaxies and then see how that varies. And so this was done in the early 20th century by Edwin Hubble with a collaboration with Westo Slipher and Milton Humason, as well as work from George Lemaitre, and they found that the speed of the galaxies, the distant galaxies, is increasing the further away a galaxy is. This led to the so-called Hubble-Lemaitre law now. And what this suggested is it's not that the galaxies are moving away from us in all directions, it's that the space between us and the galaxies is increasing as a function of time, making it appear that the galaxies are moving away from us. And this is happening for all galaxies. So this then led to the discovery that the universe is expanding over time. And one analogy that can be used to try to think about this is, you can imagine the surface of a balloon, and you have a bunch of galaxies drawn onto the surface. And as the balloon expands, the distance between the individual galaxies is increasing. And this is kind of a similar analogy to what's happening in the universe. So the universe is expanding. So that's an interesting discovery. So if the universe is expanding now, there must have been a time in the distant past when the universe was much smaller. And if it was much smaller, everything must have been much closer together. And so the temperature and the pressure must have been really high. So we can try to look for this light from the early universe and try to see do we see any evidence of an early universe. So we can try to design an experiment to look for this light from the early universe. And before we do that, let's think about light as a wave. So you can think of light as oscillations, and we can characterize light by its wavelength, which is the distance from one peak to the next peak. And then we know that all light forms this electromagnetic spectrum. So radio light, as well as microwave to infrared to visible light that humans can see, and then X-rays and gamma rays are all part of electromagnetic radiation. And as you change the frequency of this electromagnetic radiation, you're looking at different regimes of the electromagnetic spectrum. So gamma rays and X-rays have very, very short wavelengths, and equivalently, they have very, very high frequency. And they also have high energy. Whereas if you look at radio, there's much longer wavelengths, and the frequencies are much lower, but there's also lower energy. So we can then try to look for this light from the early universe from the electromagnetic spectrum, and theoretical predictions suggested that light should be in the microwave regime. So it should be roughly around here. And so this is what was discovered in 1965 at Bell Labs in New Jersey, where Arnold Penzias and Robert Wilson were working on a horn antenna to try to track satellites. And they were trying to reduce the total noise in the detectors of the antenna. And what they were discovering is that there's always this 3.7 degrees above absolute zero, or roughly negative 270 degrees Celsius of noise present in the antenna, no matter what and no matter like what they tried, so they tried to remove all possible sources of this noise, and they couldn't remove it. And what was interesting was that it was present in every direction, and it was also present throughout the year. And they tried to rule out all possible, sources of noise, such as pickup from the ground or noise from the amplifiers and the detectors themselves, and they couldn't come up with it, any explanation, including the possibility of pigeon poop in one of the antennas leading to this additional radiation, which even after they cleaned it was still there. And so they had actually discovered this light from the Big Bang. And because it was present everywhere and present throughout the year in every direction, that kind of supported this cosmological principle idea that people had started thinking about earlier, is that this light is same at every location, and it's independent of which direction you look at. And this discovery was a crucial discovery in cosmology and in science, and it led to the Nobel Prize in Physics for Arno Penzias and Wilson for the discovery. Now, a little bit of an aside, this horn antenna in Crawford Hill, New Jersey is still there, and anyone can visit it. And it's really cool to see this piece of history that discovered the Big Bang. And there's a sign there that says, Penzias and Wilson discovered the CMB in 1964, and this unexpected discovery was the first evidence of the universe, that the universe began with the Big Bang, ushered in experimental cosmology, and it's now an historic physics site as part of the Register of Historic Sites, which is really cool. It's sort of like visiting a natural history museum, but the object in the museum discovered light from the oldest possible light that it's possible to be discovered. So it's really neat. So we have this cosmological principle that this cosmic microwave background is the same at every location and in every direction, but that can't really be true, can it? So if it was the same at every direction and everywhere, and it was exactly the same, how did we go from this homogeneous and isotropic Big Bang radiation from everywhere to the formation of galaxies and structures in the universe that we see today? How is it that we have planets and people and galaxies if the initial universe that we started with is exactly identical everywhere? So that led to the realization that there must be some small changes or fluctuations in this cosmic microwave background that maybe were not detected using this horn antenna detection, but we might be able to detect them if we try to make a map of this radiation from the early universe. So we can try then to make a map of this Big Bang radiation. And then if we do that, we still see that it's the same everywhere. So it's 2.7 Kelvin of radiation projected on the sky, and it's still the same. But one of the things we can try to do is we can try to turn up the contrast of this image. And if you do that, you do see fluctuations. So now this is an image taken by the Planck satellite. And we see small hot and cold spots. You can see like the red and blue spots in this image. And these fluctuations in the temperature are 1 part in 100,000. So they're really, really tiny fluctuations in this light that we see. And these fluctuations are then what led to the formation of structure in the universe. So the formation of structure through gravitational instability. And this is a really cool discovery. And what we can then do in cosmology is try to figure out how many fluctuations are there as a function of angular size on the sky. And then if we do that, we get a plot that looks like that. And then once we have this data points, we can then try to fit statistical models of the physics of the universe and try to understand what the universe is made of. And so what we learn using the cosmic microwave background and fitting these data points, as well as other observations, is that the universe, the pie chart of the universe is, 27% of the matter in the universe is in the form of dark matter. And roughly 5% is in the form of ordinary matter. So this is matter like electrons and protons that interacts with light and what we are familiar with. And the primary component of the universe is this dark energy, which comprises about 70% of the energy content of the universe. So the dark matter is this invisible form of matter that we can detect through its gravitational effects. And then dark energy, which was discovered using observations of exploding stars and measuring these exploding stars at different distances by two teams, the High-Z Supernova Cosmology team, as well as the Supernova Cosmology Project, leading to another Nobel Prize in Physics, an amazing discovery, and also then suggesting that the expansion of the universe is not only expanding, but is actually accelerating in its expansion. So we then are led to this picture of these tiny fluctuations in the light in the early universe, seen in the cosmic microwave background. And then these tiny fluctuations then lead to the formation of structure in the universe through gravitational collapse. And the gravitational collapse then leads to the formation of galaxies, stars, and planets. And all this time, as a function of time, the universe is also expanding. And in recent times, roughly close to when the Earth was formed, dark energy has started to dominate and cause the expansion of the universe to even accelerate. So if we go back to this image of the local group of a distance of now 10 million light years, what if we now zoom out even further? What do we expect the structure to look like if we zoom out even further? And in order to do that, I'm showing here a simulation by the Millennium Simulation Project. And here, we're no longer using light years because even light years are not sufficient to represent these distances. So we're using units of megaparsec. And 1 megaparsec is 3 million light years. And what we see in this image is this cosmic web-like structure. There's these voids or empty spots, and then there's these bright spots or regions where galaxy clusters are located. And if we zoom out a little bit, we can see that there's these bright spots and that these bright regions are connected by this filamentary structure. And this filamentary structure then leads to these nodes of galaxy clusters. So if we now zoom into these nodes, we see a galaxy cluster in the simulation roughly at 4 megaparsec distance. And these are these largest gravitationally bound structures in the universe. And if we zoom out a little bit more and look at the large scale structure again, we can see these clustered regions and these like filamentary structure, connecting these cluster regions. And it kind of looks similar to the picture from the International Space Station of the East Coast, where you have these clustered megacities and they're connected by highways, allowing people and goods and stuff to travel back and forth between the cities. So what are galaxy clusters? So galaxy clusters are the largest gravitationally bound objects in the universe. And they're 10 to the 15 times more massive than the mass of the sun. So they're really, really, really heavy objects. And they're also really large. So the distance across a cluster can vary from 5 to 30 million light years across. So if you were to travel from one side to the other, going at the speed of light, it could still take you up to 30 million light years to get across. So really, really large structures. And they comprise of hundreds to thousands of galaxies each. And the actual composition of a cluster, it's 80% of the matter in the cluster is in the form of dark matter. And then roughly 15% is in the form of gas between in the intergalactic medium, so between galaxies. And because the gravity of a cluster, the gravitational potential, because of the fact that the cluster is so massive, the gravitational potential is really large. So the electrons in this intergalactic medium are also moving really, really, really fast in order for them to be bound to the galaxy cluster. And if the electrons are moving really, really, really fast, that means there's also the temperature is really high. So the temperature of the gas between clusters can then reach up to 100 million Celsius. So it's really, really, really high temperature. And then material like stars and gas within the clusters comprises only about 5% of the total matter content of a cluster. And the picture on the right is a really amazing cluster called the Bullet cluster. I'm going to talk a little bit more about that in the next slide. But you can see the optical image showing the galaxies in the cluster, and then the red image is actually X-ray gas, and the blue image is the map of the distribution of the dark matter measured using gravitational lensing. So how can we observe galaxy clusters? Well, if we go back to this picture of the electromagnetic spectrum, we can think about knowing the properties of these clusters, in what kind of wavelength regime in the electromagnetic spectrum we might be able to observe them. And so using different physical mechanisms that are happening in and around clusters, we can then observe clusters at different wavelengths. So for example, the hot gas that we talked about that's glowing at 100 million Celsius emits X-rays. So we can, have a space telescope that observes X-rays and then look for this hot gas in X-ray observations to observe clusters. In the visible wavelengths, we can look for clusters and try to learn more about them using a principle called gravitational lensing. And finally, in microwave and radio, we can use the Sunyaev-Zeldovich effect to also detect and learn more about clusters. And I will describe gravitational lensing and the Sunyaev-Zeldovich effect, which I'll call the SZ effect from now on, in more detail. So why are clusters interesting and what can we learn from them? So first of all, clusters are extreme astrophysical laboratories because of the really, really hot temperatures, the really large sizes of the clusters, and the gravitational potential wells, or the masses of the clusters, are really large. So we can try to ask the question of how many clusters are there? How much do they weigh? How does this number and mass change as the universe evolves? And learning more about that, about how the number of clusters and their mass ranges change as a function of time, can allow us to learn more about dark energy and dark matter, because dark energy and dark matter, once again, are dominant components of the universe. So if there's more or less of each of them, that will change structure formation on the large scale in the universe, which will then change the number of clusters and the masses of clusters as the universe evolves as a function of time. So we can try to look for clusters and measure their masses and their mass distributions and see how that changes as a function of time. And that can also help us try to understand whether or not this dark energy, does it stay constant throughout the universe, or does it actually evolve or change with time? We can also learn more about galaxies and astrophysics, so we can learn about how do galaxies evolve within the clusters, and do these galaxies evolve differently within clusters than galaxies that are not in clusters? And are galaxies evolving differently for clusters that are really, really far away or at in the early universe, and clusters that are present at a later universe? what is the distribution of galaxies like within clusters. And we can also learn about the environments of clusters. So these filaments and these bridges between clusters can also help us understand the formation of structure and how dark matter and galaxies might be flowing from filamentary structure into clusters. So the environments themselves of clusters are also very interesting to study. And finally, we can look for clusters that are actually colliding and merging with each other. This can also then help us better understand the nature of dark matter itself and whether or not it interacts with itself. Specifically, if you look at this image on the right, this is a bullet cluster. This is actually a colliding cluster. So actually 2 clusters have collided with each other. And what we see in the red image is that it's the hot gas that has interacted between the 2 clusters. But the blue, which was measured using gravitational lensing, is a distribution of where most of the mass is. And the most of the mass is comprised of dark matter. And it seems from this image that most of the dark matter just went right through each other and it did not interact. So learning about merging clusters can allow us to better constrain the nature of dark matter and what its properties are. So this is really neat. So going back to this image of how can we observe galaxy clusters, I'm just going to describe gravitational lensing and the SZ effect in more detail. So the SZ effect, specifically the thermal SZ effect, happens when light or a photon from the cosmic microwave background, so this light from the early universe, interacts and it reaches a galaxy cluster. So that's shown as a blue blob. So it reaches a galaxy cluster, and because the electrons' temperatures are really high, the electrons are moving really fast, and the electrons can then impart some energy into this photon of the CMB. So the outgoing photon from the cluster has slightly more energy than the incoming photon. So what that means is that the spectrum, which is how much energy the cosmic microwave background is emitting as a function of frequency or wavelength, because the SZ effect is increasing the energy of the incoming photon, the spectrum gets shifted to a slightly higher frequency. So you can imagine this dashed line is the initial spectrum of this cosmic microwave background, and as it enters the cluster, it gets boosted, and this solid line is the spectrum of the CMB photon at the location of the cluster after it's been inverse Compton scattered. So we can then what we can then do is try to detect these clusters as a function of wavelength. So we should expect to see cold spots at frequencies that are below 200 gigahertz, because this is where the spectrum intensity has decreased compared to the original one. And then we can look for clusters at above 200 gigahertz, where clusters should then appear brighter because the spectrum has increased. And this is exactly what we see. So this is an image at the bottom of a galaxy cluster taken by the Planck satellite at these different frequencies. And what we see is that at frequencies below 200 gigahertz, we see this cold spot. And at frequencies above 217 gigahertz, we see these hot spots. So this thermal Sunyaev-Zeldovich effect is a really powerful way to detect clusters and measure their properties. And it is also independent of how far away the cluster is, because the light that you're using to detect the cluster is the oldest possible light that you can observe anyway. It's the light from the cosmic microwave background. So the SZ effect is a powerful technique for detecting clusters independent of the distance of the cluster to the planet Earth. Specifically, I'm working on an experiment called the Atacama Cosmology Telescope, the picture of which can be seen on the right. The ACT telescope is located at the Atacama Desert at 5,200 meters. And the telescope observes in different frequency bands that range from a wavelength of 1.4 to 10 millimeters. And it's a 6-meter diameter telescope that has been operating since 2007. its third generation camera has 30,000 detectors, and it has lower noise and a better resolution than the Planck satellite. And it so far has detected roughly 4,000 galaxy clusters. And also, it has also detected roughly 150 candidate multiple cluster binary systems as well. And the reason that the ACT telescope is powerful is because of its high resolution. So the ability to resolve small scales on the cosmic microwave background. So this picture is taken at a frequency of 90 gigahertz. On the left, we can see the Planck image, and on the right, we can see the ACT image, and we can see that ACT is able to resolve this small structure in the image. And combining the two is a really powerful tool, because then you get information both on the large scales as well as the small scales. And what we can see in the ACT map on the right is that the bright spots are individual galaxies that have been detected in the ACT map. And the cold spots, these blue spots, are actually galaxy clusters. One of the specific cluster pair systems that I'm currently working on is this Abell 401 and 399 cluster pair system. And we found a filamentary structure between this cluster pair system, and it's really exciting. So one of the projects that I'm working on is trying to use data from the ACT telescope as well as the Planck telescope to try to learn more about the system. So specifically learn about the properties of the clusters, as well as this filamentary bridge structure in between the two clusters. I'll talk next about the concept of weak gravitational lensing. So because clusters have really, really high masses, they also have really large gravitational potential. So if we look at the planet Earth here, and we're looking at a galaxy cluster, and then there's galaxies that are behind a galaxy cluster, because of the large gravitational potential of the cluster, the light from the background galaxies gets distorted or bent around the gravitational potential of the cluster. And this leads to distorted images of galaxy clusters that we can then detect with our telescopes. So here's an image of a gravitational lens system. This is a cluster Abell 2218. And we can see the cluster in the front. So the sort of like yellowish looking galaxies are part of the cluster. And we can also see these arcs of blue spiral galaxies that are being lensed by the mass distribution of the cluster. And what we can do using the technique of weak gravitational lensing is that we can measure the shapes of these background galaxies, and then we can measure the shapes of many, many, many of them. And then we can see on average, using those shapes, we can then reconstruct what the mass distribution is of the cluster. And this technique is especially powerful because it is independent of the type of matter that caused the lensing in the first place. So it's agnostic of whether the matter was dark matter or luminous matter. So this leads to gravitational lensing being a really powerful tool for measuring the mass distribution of galaxy clusters. For that, I'm specifically working on a project called the Superpressure Balloon-Borne Imaging Telescope, or SuperBIT. SuperBIT is a near UV to near infrared telescope that is a balloon-borne telescope. And picture of the SuperBIT can be seen on the left here from our engineering test flight in 2019 out of Timmins, Ontario. And the balloon is a superpressure balloon, which when inflated is roughly the size of the CN Tower. So it's a huge balloon. And one of the questions you might ask is, why launch a telescope on a balloon? Well, there's multiple reasons. The weak gravitational lensing is very difficult to do because you want to be able to measure the shapes, the distorted shapes of these galaxies with high precision. And it's really hard to do that from the ground because there's a lot of atmospheric turbulence. So from the balloon, we can go up 35 kilometers above sea level, and where there's negligible atmospheric turbulence, and then start to take images of these galaxy clusters. There's also improved transmission of light. So this picture on the right shows the transmission of light as a function of wavelength. And these different color lines are what is the transmission as you go at different altitudes above sea level. So we can see from the ground at roughly 1 kilometer above sea level, a lot of the light from 300 to 700 nanometers is getting blocked by the atmosphere. But if you go to roughly 20 kilometers above sea level, you can start to then make these observations and get higher transmission in those wavelengths. And it's roughly even close to space-like observation conditions. There's also lower backgrounds from the sky that will deteriorate your image. And it's also a cost-effective way where you can also recover the payload. And then you can keep up with detector technology by having short development timescales. So a little bit about how the optical system works. So it's a 300 nanometer to 1100 nanometer telescope with a 0.5 meter diameter primary mirror. And it has a field of view of roughly 0.4 degrees times 0.3 degrees on the sky. And it's roughly 40 times the field of view of the Hubble Space Telescope, advanced camera for surveys, which is really neat. And also, it turns out pointing and stabilizing a telescope from a balloon platform is a really, really difficult engineering problem. And our group has successfully been able to point a telescope from a balloon platform with very high stability over the course of the years through its engineering flights. And that's really exciting. And the way the telescope works in terms of its optics is the light comes in from the left, it bounces off the primary mirror, hits the secondary, bounces back into the optics box, and then it gets reflected using this tip tilt mirror onto the focal plane where our science camera is. And then we can then make images of galaxy clusters and other astronomical observations on the science camera focal plane. The way the pointing system works is SuperBIT is able to point in azimuth or in yaw from 0 to 360 degrees. And it can also roll to keep up with the rotation of the sky from -6 to 6 degrees. And then it can also point in elevation or in pitch from 20 to 60 degrees. And here's just a short video of a SuperBIT pointing in the high bay. So you can see the instrument, its solar panels, the telescope is right here. This is one of the star cameras used for pointing and stabilization. And there's electronic boxes on the side. And it's covered with mylar to reflect off solar radiation. Here's an image from the SuperBIT engineering test flight taken, I think during 2019, of the Abell 2218 galaxy cluster. And what's neat about this image is it highlights the large field of view of the instrument. So if we compare this now to the Hubble Space Telescope, we can see how much larger the field of view is of the SuperBIT instrument. And SuperBIT is a pathfinder for another Balloon-Borne imaging telescope called the Gigapixel Balloon-Borne Imaging Telescope, or GigaBIT, which our group is currently working on, and we have a preliminary mechanical design for it. And GigaBIT will have an even larger primary mirror, and so then it will be able to detect galaxy clusters with even better resolution and with even improved sensitivity. So finally, looking into the future, there's other instruments that are coming online that will allow for even better observations of the large-scale structure and galaxy clusters. So the row on the right is in telescopes and observatories that will be coming online that will observe in the radio and the microwave, specifically the Simons Observatory, the CMBS-4, and the Lightbird satellite. And at the bottom are telescopes that will be observing in the visible or infrared. So there's the Euclid Space Telescope, the Nancy Grace Roman Space Telescope, as well as the Vera Rubin Observatory. And the combination of these measurements at different wavelengths will be a really, really powerful tool for us to detect many, many more clusters and constrain more of their properties and learn more about not only the clusters and their environments, but also the large-scale structure of the universe and what the universe is composed of. And with that, thank you very much for attending the talk. And if there are any questions, I'd be happy to answer.
Thank you so much, Ajay, for that great, super informative talk. It was really interesting. I'll start with one of the questions from the audience, and that is, how do we know that our galaxy looks like a spiral?
That's actually a really good question. So what if you look out in the south direction, you can see a plane just going up over the horizon, and that plane is part of the spiral structure of the galaxy. So basically, what we can do is we can measure stars within our galaxy, and using the locations of the stars, we can then try to back out what the structure of the galaxy would have been. We could also track the orbits and then see like where most of the gravitational potential is, and then try to reconstruct what the shape of the galaxy would have been in order for these stars to have these orbits.
Yeah, great. And yeah, I guess just another little thing to add on is, we're not in a special location. We're not in a special galaxy. So, we only see certain shapes of galaxies, and, we can then use our data to figure out which shape are we most like. Yeah, great. Okay. So we'll go to some more questions. So one would be, why is it significant that when you were talking about the bullet cluster, that the dark matter didn't interact and that it just passed through itself? And what can we learn about the dark matter from that?
Well, so let's look at the bullet cluster again. It's a really cool image of the bullet cluster. What's interesting here is that if you had baryonic matter, which is what makes up most of the gas in the intergalactic medium, and you have these two clusters that are giant clusters colliding with each other, the baryonic matter is interacting and emitting light in X-rays. Because first of all, both of them have really, really, really hot temperatures. And then they're colliding together, so they're running, like the electrons in the gas is running even faster. So the X-ray emissions is even higher. And then you can even see shocks-like structure. That's why it's called the bullet cluster. And the dark matter just happily just went through, like nothing seemed to happen. And that can allow, we can then try to then fit different models of the nature of dark matter, specifically one thing we call the cross-section, the interaction cross-section of dark matter. And then we can see if dark matter does interact with itself, what would this gravitational mass distribution look like? And then you try to change that cross-section a little bit more, and you're like, oh, look, it should have looked different. So we can try to use our models of this cross-section of dark matter, and then try to constrain whether or not there is a cross-section, and if there is, how much it could be, like as a maximum. And then using these images are really useful because we have some empirical data to compare our models with. I'm not sure if that answers the question.
Yeah, that's great. We can go on to the next question, which is, will the James Webb Telescope help in making new discoveries about galaxy clusters? And that's a very topical question, given that it actually got launched on Christmas of 2021, which is exciting.
Yeah, really exciting. So if I go back to this image here of like what we think happened after the Big Bang in terms of the structure formation, James Webb is designed to look in the infrared wavelengths. So that means that it's able to look at light that's from the really, really, really early universe, because the light from the really, really, really early universe has stretched as the universe has expanded into the infrared wavelengths. So it's allowing us to look further back in time. And that's really cool because we've never really been able to look that far back in time before. So we can then try to learn more about how do these galaxy clusters even form in the first place in the early universe. Are these just galaxies? A bunch of galaxies are coming together and hierarchically forming galaxy clusters, and then we can try to answer some of these questions using the James Webb Space Telescope. So that will be also really, really cool data sets.
Yeah, it'll really help revolutionize things. Do you want to elaborate a little bit on what you were saying about like hierarchical formation? So a little bit on like, the like smaller things making bigger things, or the bigger things then going into smaller things kind of idea that we have?
Yeah, so I think early in the 20th century, like there was a lot of debate about how structure forms, like whether you get galaxies and combine them together into a galaxy cluster in the large scale structure, or do you start with the cluster and then that cluster breaks into smaller pieces, like galaxies, for example. And empirical data seems to favor the hierarchical structure of formation, where you start with stars and galaxies, and those galaxies over time, through the process of gravitational instability, kind of combine together and lead to formation of these nodes in the cosmic web. And these nodes are where, like galaxies are flowing into these nodes using this filamentary structure. And over time, these nodes grow and grow and grow. And then that leads to this formation of this large scale structure that we see. And you can think of gravitational instability in the sense that, well, first, if everything was uniform, we wouldn't have gravitational instability. It would just be a uniform universe and nothing would form. But this gravitational instability, you can think of like, if you have a bunch of bowling balls that are equally spaced on a trampoline, nothing's going to happen, right? They're all equally spaced. But then if you move one a little bit to one side, all of a sudden, all of the other ones are going to start attracting toward it. And that kind of like instability in the initial structure leads to this instability, formation of these nodes. That's one way to think about it.
Yeah, that's a really great explanation. I guess we can, ask more of like a broader question of, what made you decide to go into this part of like astronomy and astrophysics, and like what is the most like exciting, like cool fact that you can think of about these kind of topics that you've learned?
Well, I'm one of those people that I find like many things in astronomy and cosmology really interesting. And it's hard to answer like what's the coolest fact. I think why cosmology specifically and like looking at the larger scale structure is interesting to me. It can then allow for some of the questions to be more fundamental about how did the universe form and how is it changing over time, and what is the fate of the universe? Is it going to continue expanding forever? Is it going to collapse on itself? And like what happened in the early universe? So it's interesting because it is an interdisciplinary field, I think, because there's a combination of particle physics and nuclear physics and theoretical physics and quantum mechanics coming together all the way at the beginning of the universe. And we're trying to understand, like trying to come up with a theory that works with everything. And also in terms of observations, if you think about it, like looking at this last slide, in terms of observations, we have an interdisciplinary collaborations that are theoretical, physics, coming up with predictions on what we might see in clusters in the larger scale structure. And then we have observational astronomers trying to make these observations using instruments built by, electrical, mechanical, aerospace engineers, using algorithms like often developed by computer scientists and machine learning. So like as a species, we're coming together and using our interdisciplinary knowledge to try to learn more about it. And that's really exciting, I think.
Yeah, that definitely is really exciting. Especially like if you think of all these different instruments that you've been talking about, like that's so many different instruments. So, that's a lot of different work that needs to be done. And yeah, just as you were saying, with computers, like without computer scientists and stuff like that, how could we really do this? Yeah. And I guess there's this one last question, a little adjacent to the topic. But they're asking about how the Earth is rotating. And if you happen to know how fast the Earth's rotation is decreasing, and if this would be relevant for the observation. So I guess if the time frame of the Earth's rotation changing, do you have to take that into account when you're doing all these observations?
That's actually a really good question, because, well, it's not, maybe I'll address the rotation part after. First, let's think about the fact that we are in a galaxy and the solar system is moving in the galaxy. So we're not still in the galaxy, the solar system is moving in, with a certain velocity. And if we then look at this cosmic microwave background, we see this dipole structure. I haven't shown that here, but we see like half of the sky is brighter than the other half, and half of the sky is cooler. And this is like the dipole, which means that because our solar system is moving, well, because the Earth is first of all moving around the sun, and solar system is moving around the galaxy, and the galaxy is moving toward Andromeda, and our local group is moving kind of like toward the Virgo cluster. There's all these motions that we have to account for, and when we make an image like that, we've corrected for all of those. And the way that happens is it's like, you can think of it as a Doppler effect. So if you're moving towards something, and you're observing it, the frequency of it seems higher, and if you're moving away, its frequency seems lower. So that's why in half of the sky, because of the motion of our solar system, we can see brighter CMB and then a cooler CMB in the other half of the sky. In terms of rotation of the Earth, that doesn't really matter, because if for a satellite, we're above the Earth, first of all, and we're just mapping the entire sky. Yeah. Yes, I don't know, did you have anything to add, Simran, for the rotation part?
No, I think that was pretty good. There was actually like a really great way to go from the questions into the demonstrations, because you're mentioning Doppler shift, and that is actually one of the demonstrations that we have. But first, let's thank Ajay again for that really great informative talk. And we will just try to get to the wrap-up slides. Give me 1 second. Flashing through the presentation.
Sorry about that.
Oh, no problem. These slides are great. Okay. Okay. Great. So before we go to the demonstrations, I'd first like to do a thank you to all our volunteers that helped make today's event happen. And also a thank you to our sponsors, which also allow AstroTours to continue to happen. So we now will go over to a Zoom link, which can be seen on the screen, the bit.ly one. It also should be in the YouTube chat. And these different activities will include things from Ask an Astronomer, looking at galaxy cluster simulations. There's virtual telescope tours of the James Webb Space Telescope, what the question was asked about. There's Doppler shift, gravitational lensing, and showing you how you can use Xenoverse to participate in real science. And again, please fill out our feedback forms at bit.ly/astrotours. And yeah, let's thank Ajay again one more time before we go over to the Zoom room. Thank you for the really great talk.